Hello, everybody, and welcome to Handmade Hero. We have two bugs in our lighting system, and, well, we have two bugs we know of. Sometimes with something like a lighting system, you have this nasty thing of, you have the bugs you have, and then you probably also have other bugs that you may never find, because lighting is so subtle, you may never find out, right? But we have two bugs that we know about, and so today what I'd like to do is try to find at least one of them. The one that I think is going to be the easiest to find, and of course that's just my guess, who knows if it'll actually be the easiest to find, but the one that I expect to be the easiest to find would be why we're having a problem with light copying. In order to make lighting efficient, of course lighting is very expensive. One of the things we do is we bin the lights we basically cabin off where the lighting occurs. Into just the region around where we are looking, right? So you can see the buggy lighting happening here. You can actually view two separate bugs happening. I'll stay in this region for a second so that you can see only just the one that I'm going to talk about. But, for temporarily, if you look here, you can see how we get this sort of weird light bleed that it looks like it gets contaminated by some preternaturally bright light seems to be able to contaminate the system with incredibly over bright values, right? That's one bug, and we have to go figure out what's going on there, why we're getting this sort of energy, basically this runaway energy ramp, which we didn't used to have. So we have to go figure out what that's coming from because we don't know. And the other one is this one. You can see if we're in a region where we don't actually necessarily have that particular problem, what you can see is that the copying, so as we align the lights differently as the camera, you can see the camera visible rectangle here in white, and the lighting moving in this sort of cyan frame there that moves just to make sure that the lighting is always kept within a certain region. If you notice, what happens when I do this is on the moves, it seems to almost clear out the lighting. It's very weird and erroneous, it looks like. And what's supposed to happen is it's supposed to copy the lighting forward. But what actually looks like it happens is that the lighting gets reset to black and then it gets recomputed or something close to that. And so, this is unusual and strange because we're just getting these very weird artifacts that we didn't used to have. Right. That's really, I guess, the most strange part of it is that the light copying was working fine. And then we went in and we drastically simplified a bunch of things in the lighting, which was great. And now it runs extremely quickly and still produces very high quality results. But we introduced these bugs. And so now we have to get rid of them. So I don't really have a handle on what's going on there. So what I would like to do today is figure out what that's coming from. So when we do that light alignment, what's actually the problem there, right? What are we actually experiencing that causes that strobing effect, because we would expect it not to really drop in that way. And, maybe there's something else going on there that really isn't related to the copying. Maybe the copying's happening okay, but it's something else. But given what we currently know about the lighting system, it just doesn't make good intuitive sense, because first of all, we know that the light, when we do a light probe, so when we do the sampling for a particular light source, what we would want to do is we would want to have eventually we would like to have the light probes probably be more stochastic than they are. But right now, every light probe casts the same number of rays as every other light probe. So when you shift the lighting grid, unless I'm just not thinking of something that we're doing, there's something we're doing that I'm just not thinking of, that I'm confused about, there actually should be no way to get a different lighting result than you already have. You know what I'm saying? You shouldn't be able to... you should always, no matter which point on the grid you are, you should always produce the same result for a particular location. So we would expect the copy to be completely invisible shifting the grid over should not have any effect. If we were using the grid, if we were injecting entropy based on which point in the grid you are, then you could imagine some other bug about the sampling, meaning that when you shift the grid over, you get a different result, and that could contribute to the flashing, right? But in this case, we know that's not actually happening. There is no entropy injected into the grid, so we should, no matter how we slide the lights grid, we should not actually be able to produce this result. So that's very odd, and it means there must be a bug in here somewhere. The problem is I have no idea what that bug would actually be, because we didn't change the code that actually does the copy when we simplified the lighting. So it doesn't make very good intuitive sense that you would have this problem. So if you look at how the light atlas works, which I believe is the thing that executes the copy, here's the voxel code on this side, and here's the lighting atlas code on the other side. We're looking at a routine here called block copy atlas. And block copy atlas just takes a offset parameter, and the offset parameter tells you where in the voxel you are supposed to be fetching, right? So you're looking at, like, you know, I'm gonna fetch 2 away or 3 away or whatever it is. That's how much shift you're going to have in each of the directions. Now we nerfed the Z code, so Z now doesn't work anymore, right? Intentionally. This will never happen. Why? Because the voxel never changes its Z location. It's pegged to just we removed stacking, so it's pegged to just the only part is just where the game currently takes place, that flat plane. And so if you look, this code should in theory never run, which we could, assert. So like we could say, right? But you know, one of the bugs could be maybe it does. Maybe we're pursuing there. I think I already asserted that this doesn't happen, because I'm pretty sure that in the actual lighting code itself, where we call block copy atlas, because this is the only place, we assert that the Z is always passed in as 0. So, you know, we should be relatively assured at this point that the Z code never. Okay, well, there you go, right? So that's something to investigate right there. So we're never passing a dvoxel Z as far as we know, because this assertion should fire, unless there's somewhere else that calls block copy atlas. I guess I should double check the call stack, but I assume it does. Yeah. So if dvoxel dot Z here is always 0, what is happening, right? Z should always be equal to stop Z, I would think. Although, actually, you know what? No. Now that I think about that, that's probably wrong. The Z might still consider itself happening on one layer. Yeah, so that's the Z region. I take that back. That's what should actually, the one that should not run is this clear. So basically, this one should run, because this is actually the loop for Z that does get copied, that does get written. This is the loop for Z that doesn't get written. So this is where you would, you know, it would just be off, right? It would be zeroed. So this is the actual one that should never happen, because the zeroing should never occur. So let's try that one more time. Okay. So I feel like that should probably never happen. I suppose it's possible that we never get in here, but that should probably never happen. So let's just check in a debug build so we can inspect values reliably. Which would be this. And so let me see, because I don't understand why this would be happening, since, you know, I would assume that that this should not be occurring. Like, we should not be shifting Z, and maybe I'm wrong about that. But, like, if you think about what happens with the fetch offset, the fetch offset should always be passing in a 0 there, which it is. So if it's always the case that you're not moving at all in Z, I don't think I understand how this clearing code would be working, right? Like why would we ever be clearing an entire layer of this thing? It doesn't make sense, does it? I mean, at least I don't think so. So that, if that's the case, that's probably just our bug. We accidentally always clear one layer of the Z, I guess. Maybe because these computations were actually wrong and we just didn't see that because the top layer of Z was never visible before. You know what I'm saying? So it's entirely possible that the problem here is primarily such that we've got a bogus computation in how final Z works, and what's happening is that the topmost Z layer will always like this computation was one off. So the topmost Z layer, you can see internally here that even though we said don't move in Z at all, it's going to clear one entire Z plane. So I'm going to go ahead and say just right off the bat, before we even look at it, that if we if-zero this out, I wonder if that just completely fixes our problem, right? And if it does, that tells us that that's what the bug is. The bug is that there's like an off by one computation in the Z there. Well, I should probably run it in release mode. But that would totally answer our question, right? If it turns out that the top Z layer is always getting cleared, that's just obviously wrong. And that would produce the flashing. So let's see if the flashing goes away. Of course, it's hard to tell because we have the other bug is happening as well. But let's see what happens. I can't, it's a little bit hard to tell with the lighting voxels in there. So maybe I should remove the lighting voxels for now, since we don't really need them for any, we're not using that. Like I don't really need to see that for any particular reason. So maybe I should just go ahead and delete that. That's the spatial, there's like a draw spatial grid, this thing. If I just remove that. There we go. It should be easier to tell if there's any flashing. I mean, it's still a little hard because since there's the other lighting bug, it's difficult to see. But we just have to get to a place where it's less, So I would say I still see it, though. I still see at least some flash occur there, which is not just that. Now, of course, I don't know if we're doing some kind of a weird... There's some weird other artifacts happening there, so I don't know if we're still seeing some other kind of weird aspect to it. The fact that the light has that weird, like, this light gets brighter when I move makes no sense at all. So there's a lot of really weird stuff happening. So I feel like we've just got some core things we messed up when we did our simplification pass. And so, it's a little bit hard to say. So are we still getting that flashing or not? It's really hard to perceive. Which makes it a little bit difficult. I would say we're still getting some flashing, just not as bad, but there's still some there, right? Like, I can still see the light shift over. So it seems like it's still copying wrong. Like, my assumption is that the clear makes it so that you don't see that artifact, but it still seems like maybe the values getting passed in are incorrect. Do you know what I'm saying? Like, that part seems broken in some way. I'm not exactly sure what that way is, but something odd is happening there that is an issue, right? My assumption... Oh, well, actually, you know what? It's pretty obvious what it is, actually. There's at least one other one. which is that this copy is only happening at the lower level because we know for a fact that final z is not the correct value. So actually, yeah, we would still see half of a problem, which is the upper level is not sliding, right? So that's exactly what we would expect to see. Okay, so what's going on? Why is this happening? So if we look at this code here, this is the code that computes the z values. So you can see stop z and final z occurring here. So let's take a look at how this stuff shakes out. So we can see the two paths involved. The dz value in our case So I guess looking at this, like the initial z value is going to run to 0 to this equation, and this is the problem that we have. It's going to be whichever is higher. The initial z, which we know is not higher because it is 0, so I'm not really sure what case that's designed to prevent. I guess just one where the dvoxel value is very low. So this is just clamping. It's saying the stop z value is going to run from the initial z to whatever the last value is. And, doesn't that just seem wrong? Where is this 1 coming from? Because look at how this code works. I guess no. Okay, so no, I'm all right with that. Because let's think about this. So if voxel dim in this case .z is 2, you subtract 1 from it, it's 1. Dvoxel z should be 0. So stop z should be 1. And I guess okay, but I do see the problem here. If this is z is not equal to stop z, the problem here is it should run this loop for the last one, right? Stop z should get, we want to run on stop z as well. So shouldn't this, if this is the one we're going to stop on, it should actually be 1 higher than. So this is as if, rather than stop z, this is computing like what the last z value would be. So it should at least be that, I would assume, right? I mean, I really just don't see it. I guess I don't understand where the -1 came from, and it seems like it would be wrong in all of these. And I'm guessing we just never noticed because we had a large enough stack that it wouldn't be an issue if to just miss 1, right? But I don't know. So we'll see. I still see a little bit of flashing in the movement, so I don't think we quite fixed it, whatever it is. But I do think that's got to just be wrong. I don't see why that would be occurring. Now, we probably should put some asserts in here. I don't know if we did that already. Yeah, we have the light atlas assert that we can turn on. So let's go ahead and turn that on so that we have some validation about what's going on here. So yeah, that's the light leak assert, but, I can probably turn those off at the moment. That's the one that catches the light leaking. It's the one that basically you validate that the values are all relatively in bounds. Yeah, so we're always going to hit that light leaking one, and I suppose what I should probably do is mark these in some other way. So I should probably do like if temporary or something like this. So just so I can find them again if I'm removing some of these, because I want to put them back in. That's the same one at the end of block copy atlas. So our light leaking checks are obviously working quite well. They catch that green thing. It's obviously very visible in the data, which is also good, I suppose, for when we go to hunt it. Okay, so at the moment, we're not fetching out of bounds at all, right? Because this thing would have asserted when we go to do zero tile or copy tile. At least I believe so, and we should probably verify that. But so I think this code is wrong. I think all of these wanted to not have the -1 in there. They all want to do the last row, which before they simply weren't doing, and that seems bad. So yeah, like oops, I guess. And so I don't think there's any problem with that now, except I still don't see the flashing still seems to be there slightly, right? I can still see, like when I look in here, I can see movement across the tile. And, honestly, there's something even weirder about that, which is the movement that I see across the tiles now is stable. So it's not actually flashing, it's like actual movement. Which again makes me wonder, how is that possible? Because there shouldn't be any way to have that happen unless we are injecting entropy. Like that doesn't make any sense to me. Like that should not be possible to be stable. To be specific about what I'm looking at here, so take a look at what happens. For example, there you can see right there, there's like a dark, like that's darker than say the two neighbors, right? When I move through, you can see that darker piece move sideways. It slides, right? And that should not really be possible because again, like I said, as far as we know, each light probe is sampling uniformly, so there's no entropy being injected based on the grid location. That must be either an erroneous assumption, meaning we did accidentally forget and leave in some kind of a permutation that's based on which grid square you're on, in which case we need to go find out where that is because we at least need to know about it even if it's not an error. But separately, that's definitely it's definitely not something we want to show up as a slide like that. Now, it's possible that if you turned off, right now we are literally recomputing all of the lighting. There's no blend factor, right? You can see here that we had previously had a blend factor. This is a blend factor, right, of like 4. That allows it to smooth over 4 frames, which I assume that if we turned that on again, maybe this would not be an objectionable artifact, meaning I don't know, maybe you wouldn't actually see you wouldn't actually see the difference, but and you can see that it does smooth it out quite a bit, but I don't know. I still see it shift almost immediately. Let's try turning that up quite a bit because maybe this will give us a clue to what is happening here. Because if I go ahead here and change it to 1/60 so that it's a very slow run, this will take an entire second to update the lighting. What actually happens to that slide? I would like to see. So it does look like it is actually based on the fact that the lighting gets recomputed differently. It looks like, right? Because you can see if I wait here, the darkening comes back, right? If I go in there, and I should probably turn all this crap off as well, which is actually not that hard to do. We can actually do it without actually changing anything here by just moving this out of here. What that is, I don't even remember. We should probably get rid of that as well. But you can kind of see here. You're like, what is that? What is that yellow? We don't even, what is this yellow box? I don't even remember. We draw so many debug things while we're trying to find situations like that. I don't even know what that box is. Is it some... Is it like a debug light? Or is it like drawing the debug light or something like that? This is where, like, the recording would be helpful. We could go back and look. It's probably not anything. It's bigger than the screen bounds. Yeah, it's not that. So I don't know what's drawing that. I have no idea what's actually drawing that. Let me just look for things that have that color pattern. So we can, I don't know, see what it is. I'm not sure. What? Well, it looks like for some reason, and we'd have to go back and check the tape to find out why, it looks like for some reason we're drawing a negative 1 to 1 cube. We were probably just trying to figure out where the world origin was. And I don't care about that even in the slightest at the moment, so let's get rid of that. Okay, so now we are free of that. So what I was trying to say is that if we look in here, and we, like, as we kind of shift in and out, with a 1 second delay, you can't see that artifact anymore, but it's still there, and that's what allows us to know that it is actually, like, that the lighting gets computed differently. So if we're zoomed in here, you can see that these light panels, after they have a chance to normalize, they look fairly uniform. There's maybe it's slightly darker in here, but only slightly. If we then move out, you will watch these darken significantly after the shift. And I don't know if that maybe is expected because they're picking up light from where the hero is standing, right? Like you can see here that as I move in, you get that light difference. But so I think what that says to me is I should turn off the debug light so that we don't actually have that happening. Like, let's just get rid of the debug light entirely, so that it's not there. And now let's see if the artifact remains as I move around. And I'll turn off the 1/60 blend as well. Let me also get this out of the way. Why I actually restarted the game, I have no idea, since I could have just left it running, but, you know. So I am not bringing a light into the room anymore. But it sure does seem like just me moving in here creates sort of synthetically more light for no apparent reason. What I will say, though, again, this just reinforces my decision that I think it was right to just, like, fix the current lighting that we have and smush it to 2D, which is what we did. Once we get this debugged, like, oh my god, this looks fucking awesome. Not for sure. This looks awesome. Like, this lighting looks so darn good. It's completely, like, it totally sets the mood properly. It has all that nice character to it. It looks great. So I do think, like, we did the right thing. Like, this looks awesome, and it runs at 60 FPS, I think, just fine when we actually do a full release build. It just looks great, right? Like, it just looks great. So yeah. I'm really pleased with how the lighting came out. I thought it was sucky at first, but it turns out it's actually quite good. It just really looks cool. Yeah. So anyway, and also, you know, the other thing I would note is that you can see that, like, when we slow down the blend, you can also see that the light contamination takes way longer, which is what we would expect. Like, in here, right, the green bleed from outside, you can see how much longer it takes because because we've slowed down the blend. It probably should still happen. I mean, if we just sit here and wait, presumably the green blur eventually will, right? It's already starting, right? You can see it's really bright here. So the power feedback problem that we're having, which we don't really know where that's coming from, which is another bug we have to fix, is still happening, but that delay makes it harder to see. Okay, so now that I've gotten rid of our light source, if I turn the blend, like the blend rate back up, where is my tea blend? Sounds like when you take a bunch of different types of tea and blend them together. I thought it was 1/60. Oh, it's not. Wow, it's not an F for some reason. All right. So if I turn this back up to just say, okay, I want to see new lighting every time. So you only get one frame to compute all of the lighting, no blend, right? That's really interesting. Now, I can sort of understand why these lights go away, and that's because the lighting is not big enough to encompass them, probably, right? So if you look at where the bounds, the lights shift out of bounds, which means we probably have to fix this lighting to be a little bit more centered than it is. The reason we had it going this way was primarily because we wanted, when the lighting was slower, we wanted to, because you could see further in this direction, we wanted to cache this in there. But it's not a very good idea anymore. We probably want these bounds to be fairly uniform around it because the lighting is very quick. It updates very fast now. So we want to keep lights, some of those off-screen lights, in bounds, right? That's what's happening there. But you can see, like, especially from the fixed view like this, you can see how it really does change. The lighting just changes as it moves. It doesn't really make any sense why that would be the case, and it doesn't really seem to be related to the copy. Because as you saw, if we turn down the blend rate, the copy happens instantly. The blend rate is not involved in the copy. If the copy was the thing producing this result, then turning down the blend rate would have not affected the visibility of this bug. So that means there's something actually different, like there's literally something different about the casting as you shift the light voxel position, which should just plain not be possible. So that's bug number one for us now, because it looks like the copy is just fine. Like, it's actually, there was a bug in the copy, we did fix it, it's gone. But there's now a different bug that has to do with sampling that is really weird, right? So we got to go track that down. Trying to think if there's anything else to say about this, but I think that's about it, right? We should probably fix that alignment. This should probably get straightened out, and I'm not exactly sure how we want to do that, but like when we do the lighting alignment part of things, so when we call update lighting, right, like we have in here, I guess I would say I'm not sure to what extent this, I think this is always the thing that actually determines like where it is aligned, right? So you can see like Vox camera offset Y plus 2, that is that hard-coded shift that's baked in there. So like if that went away, then at least it would be centered, right? So if we look now at how the blue is related, you can kind of see that it's lined up, right? Now, why we get the sort of skew on the sides so that it's biased, why we have an uneven X layout, that I'm not sure about. It might just be because it's 2 here and 1 here and it can't be made even. That I'm not sure about. But keeping it even like that, you can see fixes the room getting dark before we, problem, right? I don't think it would necessarily fix it this way because it looks like the gap, X gap, is maybe a little bit too small there. So we may have to enlarge the lighting region slightly, like one more tile on the X axis or something. But in general, I would say, So I think I'll look at how to do the expanded alignment later. So for now, I'd just like to keep focusing on this. So we have like a really strange kind of bug there, right? That I'm not sure, I really don't quite know what is actually going on. So something about the way the casting is happening is permuted based on where you are, and that shouldn't really be happening. So that's very strange. So if you look at how we are doing that in grid raycast, I thought, and maybe this is very incorrect, but I thought the way this was working before was that it shouldn't really have mattered which one of these you were, because the ray directions should all have been like the same. And maybe that's not really correct because you have different alignments versus the spatial grid, like with the quadrant index thing here. That's kind of a good question, and I don't really know. I also think we may, one other thing we could do is get rid of the 2x oversampling. We don't know that we really need that for any particular reason. In fact, we may just not want that. So it could be that we should get rid of that. But separate from that, if you look at what happens here, our sample direction table is always the same table, right? So no matter what cell you're on, I don't quite see, you should always be casting the same set of rays. That's all I'm trying to say. So in here, we loop over the entire table of TY, TX, and ray index, the full complement of rays that are going to be cast. They get cast off of the same base sample pointer, right? So, like, I don't fundamentally know why you would see differences there. It's not... It's not clear to me. Now, it could be because this walk table is kind of busted, right? So, let's suppose the walk table was busted. Then the quadrant that you were in would make the difference, right? So it could be that that's what happened. Like the light sampling walk table is built wrong or something. And like... I mean, I guess we should probably go look at that. I can't think. Unfortunately, I don't know of any way to really fix that. In like a short term, you can't just set this to 0 because then it will actually cast wrong because the location that you're casting from would be incorrect. Um, so like I'm not sure of a way to take it out of the equation temporarily to see if it is the problem. So that's unfortunate, to say the least. But we have a bunch of options here. Like one of them is to remove walk tables entirely since Z transitions are no longer an option. One thing we could do is just put the walk, because you can literally only choose to move one cell in X or one cell in Y. That's all you can do. We could probably change it so that it happens in line now and doesn't actually involve a walk table. Before that was demonstrably slower because it had to do a full 3-way XYZ check. But if you only have to do X and Y, that might be enough to fix the problem, right? To make it not too slow. But looking at this, right, this is the code that you would expect to be sort of wrong if that was the case. Okay, so wait a minute. What is this about? Is this another bug we had that we just didn't know about? I mean, it's pretty easy to have bugs when you only work on something once a week, so I'm not going to be surprised if it is. But how would this have worked? Because if the walk table offset, so every time you loop over these, when you look at how many sample directions there are, you're setting a walk table offset that overwrites whatever the previous one was. Clearly, you would need 4 of these, 1 for each of the quadrants that you were in, and the offset would have to match. So that's probably just the bug, and we didn't know we had it before, and it was just wrong. You know what I'm saying? Like, this would have to be this, where the quadrant index gets written into, like, you know what I'm saying? So in order for this code to be at all even slightly correct, you would need that to occur, and you would need your sampling spheres, right? This walk table offset would actually have 4 entries, 1 for each quadrant. That's just science. So I'm pretty sure that was wrong. Well, I mean, I don't want to say that for sure, but I'm pretty sure that is just flagrantly wrong. Like that's just completely broken. Now, since we have the weird light contamination problem, it's hard for me to know for sure, but I'm pretty sure that was just wrong. It doesn't seem to have really changed anything, which is weirder still, right? But that was just an error. I can't see any way that's not an error. Right? And this is wrong too, right? So actually, wait, no. I'm wrong. So we do actually create a different table for each quadrant. But the walk table offset's going to be wrong. So no, I'm still right. Because even though we create a different table, who cares? You still have the problem of each, you need the right index depending on which table you were using. But I think that does mean this code is now correct, meaning the fact that this dest index gets reset to 0 is totally fine because you are creating a separate table for each one. Again, you can kind of see why this code now feels like we're doing too much work, right? When there were three spatial directions to walk in, maybe this made some sense. But when there's only two, it feels like now we just shouldn't need to do this, right? Like, it feels like if you look, all of this stuff that was for loops before, it doesn't need to be loops. It can just be a single if to see if x is greater than y or whatever. I feel like it should be relatively straightforward to just say, like, not do this. It just seems like way too much work now. And I guess I don't know if this is the right time to do that, but the question is, do we bother debugging this, which I think is part of the problem, or do we not? I guess one thing we could do is if we stuffed a known lighting value into each light cell instead of doing the grid raycast. That would probably let us see more clearly if that was the case, meaning if it was the fact that the rays are different, that's the problem. But then again, I don't know. It's a tough one. It's a tough one. I don't have a very coherent thought on what the best way is to proceed, because I do think we risk debugging something that we don't want to keep, and that's a bad decision usually. On the other hand, it's possible that it won't fix the problem, and in which case maybe the problem becomes harder to find. So it's just really hard to guess. But you can see that the problem is still there, right? So it wasn't that. And another option is maybe we could try to lock the grid to only move on 2 steps. So like if, for example, if we forced the grid to not change which quadrant anything was in. So in other words, like this part, right, where we do the where we do like the center P nonsense, and we look to see, like, you know, if we need to check set the dvoxel thing to whatever it's going to be, and blah blah blah, right? If we always like forced dvoxel to be on 2s so that the quadrant doesn't change, presumably that would do it. The dark spot does move, though, is the thing. Just checking chat for a second there. It does move. You can see it. It might be hard to see on stream, but it does, right? So watch. Do you see? Like, watch those panels. We definitely get some weird, like, oscillating behavior there, which we don't have an explanation for. And it is varied. It varies as we slide, right? If you look at what's happening, you can see the slide. Well, the reason it nothing changes while I'm in the room is because I don't have a light over my head anymore, right? That's why we were getting a change while I was in the room, is I was carrying a light with me. Once we turned that off, it's pretty clear that it doesn't actually change unless this lighting volume changes. And even inside the room, you can see that it does change when the lighting volume changes. It's a little bit hard to see, but like if we fix the camera there and you look at that, right? It gets darker when the lighting volume alignment changes again, right? So you can kind of see that, like, there's definitely some really weird stuff happening there that we don't have an explanation for. So it's definitely a bug, and very unlikely to be, like, actually something correct going on. I think it's just we have made some kind of error, right? And we don't know what it is. So there's something going on with that alignment that's very strange, and I don't know what it is. And so we probably, we got to have a better way of investigating that. I do think the walk table offset stuff was definitely, had to have been broken before, because it just doesn't make any sense how it was working this time. And again, I don't know if we just want to rip this stuff out. My gut instinct says we do. Like, we just don't want walk tables anymore. Because again, it's just too much complexity for what we're doing, where we don't actually have like, I feel like we should be able to simplify this enough. So if we look at what happens for the the cell stepping, what we're computing here, right, is we have the inverse ray direction, and we just are stepping, like, we go into this cost loop here, and all we're doing is we just multiply by that inverse, and then we update. And it seems like that should be pretty straightforward to do. Like, basically we just compute two of these and we see which one is less. You know? Whichever one is less, you then just, that's the step you take. So I think that's about it. It's just a really tough decision. Do you want to use these tables or don't you? It feels like you don't, but at the same time, it's like tables are almost always faster than anything else. So you're gonna pay some cost for it. It ain't gonna be free. You know? You're gonna have to do this twice. So you have to do two subtracts, two multiplies. You got to do the compare, and the compare has to, like, then do a dependent add, and then probably the most expensive thing is you have to then look to see what you are planning to do, right? So do we think that will actually we know when we hit the apron, but what we don't know is when we go outside the Z bounds. Yeah. I agree that frou-frou is a great variable name, so that's staying in. So I don't know. I'm really kind of conflicted here. I think maybe we just pull this out. Because why should I spend my time debugging it when I think probably the correct answer is we would like to get off of this concept of using the light stepping tables, because I would like to be able to move to a stochastic system going forward that maybe doesn't rely on the sampling spheres either, because I'm just afraid, like I'm definitely afraid that we will need to vary the over time. Like now that we're able to hit such a high sampling rate, I feel like we want to use more than a table's amount of input for it. So that's just kind of why I'm sort of pushed in that direction. So let me look at grid raycast and see what I think. So inside grid raycast, here's the setup code, right? Why that code is not in a grid raycast debugging thing, I don't know. But, you know, what are you going to do? So when we do our setup here, right, we're loading up one of these RAID directions, which we know what it is, and then the walk table is used here. So when you look at how the walk table is used, it's really just one thing that it does, right? It also looks like this was the code that for stepping maybe before, like we had some code in here for stepping that we don't use anymore. Or something like that, right? Like so we previously, right, we're doing it where we didn't use the grid, and you know we computed like a stepping value. That stepping value has probably been removed now, right? But we could, you know, we recompute it, and yeah, like looking at this code, right, you can see that it was, you know, it had to do a lot more work because it was trying to do these wide and all that, which probably was pretty tricky because then it has to load not wide, so it has to move it out of there, right? So yeah. So maybe we just look at what this looks like without, you know, like if we were to, we've also kind of got this cost metric here, which is how many tests we've performed. And I guess I, again, don't really know to what extent we want that to really be a thing either. So if we imagined like how we would be remaking this routine, the exit on the cost metric would really probably not happen. Probably what would happen is we'd just do a loop and say, look, we're going to check this many cells. So every raycast gets to check, you know, 6 cells or something. And if you happen to terminate early, then fine. Like if you exit, if you leave the Z layer, then, you know, fine, right? So, you know, this for loop would probably just be more like a for, you know, however many the cost is. So, you know, rather than this solution max cost per ray, that would actually just be, and we could do this, like, we could do this sort of without actually, without actually removing the walk table first. We could simplify this part down with the still running version that we've got right now. Not that we can really test it because it's too buggy, but, we can sort of say, all right, if we were in a place that was relatively stable like this, and then I go in here and I say, oh, yeah, like, instead of this loop, what we're going to do is, like, grid sample index, or grid walk index or something, right? Grid walk iteration. And I just, like, hard bound that. And I say, look, it has to be, 8 grid squares is all you get, no matter what happens. Presumably the lighting doesn't change much, right? Like, presumably it's fine. And, basically looks the same as before. And then if we just remove the cost metric entirely, so cost metric is gone, like, it just doesn't, we just don't have it. So, and all we do instead is check the, the spatial grid node terminator thing. In theory, like, we should be able to just preserve the lighting as it is with no cost metric, because we just don't really have that anymore, right? So we're fine, and there's, same lighting running in the same way. So So really the question now is, like, let's suppose even with the walk table involved, if we wanted to exit, what we want to do is have an exit criteria that just says that you're going to exit when you leave the spatial partition, right? And the way that we did that before is we said, well, whenever you hit there's like an apron, so that when you sample that node, you can tell that it's got, it's marked as you've left, right? That does seem sort of good, but the problem is it doesn't really help us with our Z part of things. So I don't really know, like, is that actually the best way to do it? Like, is that actually the fastest way to do it? Or is the faster way to do it to just look to see whether the grid index that we were using, because it's worth remembering that now we could just keep 2 separate grid indexes as well. Like, it could be that we can just use 2, I don't know. Although, maybe there's a good reason not to do that. But because it's not 3-dimensional anymore, it opens up other possibilities. We could make it so that, for example, we just say that, the thing is 16 in one direction, so that the bottom 4 bits are the X, or, stuff like that. So I don't know. It could be that this is still the smartest thing to do, but you need one more check, which is to see whether or not you've left the Z range. And, like, that's broken right now. It's been broken since we simplified it to not use Z stepping at all. So we know that that's currently wrong, and the question is just what's the best way to fix it? And I don't know. So in terms of that, yeah, I just don't know. But at this point, we could just say, well, okay, that's going to be sort of busted anyway. Let's just focus on welding this code in there so that we can do it without a walk table. Right? So if we were going to do it without a walk table, then we just do the reverse process of what we did when we introduced the walk table, which is to say that we know the starting location, because the starting, within a cell, we know the starting location because it's, given to us by the quadrant index. So because we have to know the quadrant index to begin with, and I assume it gets passed in. Yeah, we know the quadrant index, so we kind of know how to set it up. If we I'm just trying to think. If we assume that we're just going to take and record this as a separate value that we keep through, I'm just trying to think of whether you want to go, okay, we're going to raycast and we're stepping through the grid, and we just use one value to step through the grid, and we make believe that like the origin moved each time, or are we doing something different where we just store, I think we probably just store the differences, and we track the differences as they go, right? Basically just a standard kind of Bresenham sort of a whichever error would be larger kind of a thing, right? So we check the grid that we started in. We like So it occurs to me that the way that we're doing this, we currently do it as an actual forward step. That's how the walk table was computed. What I'm wondering is, could we not do it in a way that was actually a forward check? So we basically just look at moving to the left, or like we look at changing x by 1 or changing y by 1, and we just see which one would be a better choice, exactly like you would do with like a Bresenham algorithm, right? And my only question is that conservative Bresenham, like, I'm less familiar with that. I don't really remember ever having really implemented code like that before. So I'd have to maybe look to see what a conservative Bresenham algorithm looks like, meaning one that fills all of the squares that the line passes through and not just selects, like one that cannot move diagonally and that always picks the one the line actually went through. I think that's probably what we should be doing. I think probably the stepping version we're doing here might just be overcomplicated, right? If we just tested the center of each cell to see which one was closer to the line, that just gives us the answer, which should just work. You know what I mean? So it feels like that would be all you would really need. And again, like, the reason that I'm worried about this from a tape, if you look at how the table driving works, the reason the table driving is nice is because you don't have to actually keep X and Y indices at all. You know what I mean? So it definitely introduces a fair amount of overhead because the actual X and Y indices that we step through, they now would have to be tracked. So you would have to have, right, like this sort of a thing. Whichever cell you start in, you would have this, and then in here you would need a thing where you, when you load the spatial index that you're in, you would have to build the grid index from those two values, which costs you something. And then to know which one that you move to, you would have to do the actual math. You'd have to say, look, okay, I know that the two options that I have are right look like that. They probably have to be, again, like, they probably sort of have to be in float, like you would still also have you'd probably have at least this many things. And I'm trying to think of, like, you know, they could probably be packed. So f cell x and f cell y could probably be together. But you'd have this problem of you'd have to do the computation where you actually check to see whether or not you are, you know, whether or not cell x plus d cell x or cell y plus d cell y produces a closer match for your line. And so I'm just a little conflicted because I'm like, can I get that down to be small enough that it's going to be as fast as, or at least comparable to, the speed at which you can do it from the table? You know what I'm saying? So I think that's really the part that's troubling me. So, like, how fast could you realistically make that check? Because you have to do something like, you've got this stuff, and you want to compute the which one of these is going to be better. So you have some, like, line equation, right, that we would have to determine what it actually is for this ray. So it's it's going to be the ray, and you see how far you are from the ray or something like that, right? And you're going to have to compute f cell x plus fd cell x f cell y, and then the opposite of that. So you're going to have to compute, like, for these two, which one of them will be less error. Like, will it be less error to go to this one or that one? Now, probably we can see we'd expand these two line equations out. This is, again, just standardly what you do with Bresenham, right? We would expand these two line equations out and see what the actual different factor is between them, and then we just compare those two factors, and that's which direction we step. So I suppose we probably have to write that out. So if you look at the ray direction, the ray is already normalized. So I think I'm just going to have to write this out equation-wise, right? So if you think about these two in space, you have a V3, and that's one V3 is equal to this, and I guess technically it's a V2. But we can think of it as a V3 for now, that just we then don't care what happens to the X component, right? So we have a V3, which is like the current cell location. So I might just say this is the current cell P plus one step in X. And this is basically just, it's either positive or negative. It's either one entire voxel distance in the X coordinate positively or negatively. This is where we would end up, right? The Y step P is going to be the same thing, but for Y. And we only have to consider one of these because every ray will either be 1, -1, or 0 on each of these, right? It's stepping either one voxel in that axis, forwards, backwards, or none. But it can't do anything else because every time you move one grid square, we never hop. There's no such thing as a ray that can hop across, right? So if we take those two, right, then the next step would be we would say, okay, the difference, like the delta between those two is going, from the ray's origin is going to be these two both would have a local version that's whatever they were minus the ray origin. And you can already see that we will be able to simplify that completely by just pre-subtracting whatever the curr cell P is, pre-subtracting the ray origin from it, right? So we won't have to pay this cost at all. You can already see it ahead of time because it's just a constant that's always subtracted. So that'll be free. This part will be free. And once we know where these are relative to the ray origin, then we just have the question, well, okay, how far away are these from the ray? Like, which one is closer to the ray? Now, the simplest answer here would be that, in terms of like thought, the simplest answer for thought-wise, right, is the cross product between the ray direction and one of these. So if you just took the cross product between the two of them, then you know that the length of that, so whatever the length is of this, of the cross product between them, the length of that is going to be equal to the length of the ray direction, which is 1, times the length of the local x step P, whatever this is, right, times the sine of the angle between those two. That's just the definition of the cross product. I'm sure we've covered that on Handmade Hero at some point way in the past. So we know the length of the ray direction is 1. So we know that this comparison here is just the local x step, whatever that is, times the sine of the angle, which I believe would literally just leave us with the answer we wanted, right? Meaning the cross product between these two actually tells us how far away from the ray you are, right? Because this is the hypotenuse of a triangle, and this sine, so, you're basically just constructing the leg that projects you onto the third leg of the triangle, which was that part we removed, right? Now, we are only comparing these, so we actually don't need the length. We could just do the length squared, which would be much simpler, right? Because we're just going to compare two of them together to see which one is larger. And furthermore, we know that we don't care what the distance is in Z because we're only stepping on a 2D grid. So the cross product actually would only have the other components to it, right? It's really a perp dot product, which is much simpler than the full cross product. It's, 2 by 2 instead of 3 by 3, right? So I think we're literally just comparing these. And if you look at like the, we don't have a perp dot product. We just have perp and then inner. But it's the same thing, right? So if we wanted to measure this distance, we could just take perp of the v2 version of these and go from there. So let's suppose we did that. So first of all, like I said, we get one reduction for free, which is these are all technically v2s because we're not stepping in z. We literally don't care what happens to z at all. The only question is, do we ever end up stepping somewhere where the z is where we've left the cube entirely? And how we track that, I just am not sure. Like, there's gonna have to be something that checks that is as fast as we can make it, where we just see if, like, the t value, probably what we do is at the beginning, we figure out what the t step is that gets you from where you are to outside the grid, and we just check to see whether we have gone past that t value. Maybe, right? Maybe. I don't really know. So we don't care about this part. We just care about this. And honestly, this can just not, we don't really need to use this because since we are not in 3D, we can really just use the inner product like so. So we just do the perp dot product and the perp dot product between the ray direction and whichever one of these we're looking at, like so. That will give us the distance projection exactly. Right? Like, that's just literally the distance, period. You don't really need to square it or anything, right? It just is. That's just the end of the story. So you get the exact distance from the ray to the cell center just with inner perp. That's it. So what you're looking at is you're looking at the difference between the inner perp of each of these. And you're just going to do something like this. You know what I'm saying? Now, you may have to, like, absolute value this. I have to think about this for a second, because the perp of the ray direction, we don't care whether it's which side of the ray you're on. So this is going to have to do an abs, right? Like, it's going to be like this. And we could choose to square it, like, so we do kind of have to square it in the sense that we have to do something that removes the sign, but it doesn't actually have to be squared. It can just be abs if we want. But fundamentally what we're looking at is that. We're going to look at the absolute value of the inner product of the perp, right? Perp is free. It's not actually even an operation. It's just going to change how you're computing the inner product in this case. So the inner product, as we know, like if we look at what one of these actually equals, so the inner product here, as we know, is just going to be the components multiplied by each other. And the perp is negative AY AX, right? So the perp, no, don't ask me why we parenthesize that the way we did. It's totally not correct. Perp is just on the ray direction. So the ray direction in this case, we're actually doing an inner product not quite with ray direction, but rather with negative ray direction y ray direction dot x, right? That's the actual vector that we're using here, and then local step x, which, you know, the one that we're producing here, like so. Right, is we're doing an inner product between those two things. So we actually have something that looks like this as the two quantities that we would need to compute in this case. And we're going to compare the absolute values of those two things. Now, looking at this, it's worth noting that local step x, in this case, is the current cell P plus the D cell X. I don't know if that can be simplified a little bit by saying, well, we're just tracking, as we step, we're just tracking differences here. So I'm not sure if there's something that can be done there to simplify that a little bit. But if we do this, so I don't know if that's like what we want. I'd have to think about that a little bit more. But if we look at what these boil down to, it's actually very simple, right? It's just going to be the following. So in terms of what we're actually computing, on one side, if we wanted to take the local step x, this is the x step. The y step is the same thing, but it's literally just multiplying a different value, right? So what you can see here is that as we work this through, it gets down to something very straightforward. We're literally just computing the difference between these two values. Comparing these two values. And they do have to be like absolute valued. Like so. But otherwise, they are trivial to compute. It's like 2 multiplies, 2 adds kind of a thing, right? So we're just doing 2 multiplies and 2 adds, and then, arguably we've got one more add in here, although we should probably actually substitute these in and see what that ends up being first, because maybe that turns out to actually just get taken out of the equation, right? So let's try this one more time. Let's take a look at, and you can see why the ray origin gets factored out, right? So if we were to plug in, let's do one step of plugging in here. If local step x has the minus ray origin built into it, right, then what you would have here is these x's are now going to be like 2 x's, right? So each one of these will have like a ray origin x built into it that's getting subtracted out, and both of these will have a y that's getting subtracted out, right? But what you can see here, hopefully, is that that doesn't actually change depending on which equation you're in. So if I distribute these multiplications out, all that's going to happen is I'm going to be left with a subtraction that is constant between the two things. Like, when we multiply this out, we're just going to get these two terms again, and then we're going to have out here on as a separate thing, we're going to have the ray origin, right, multiplied, if that makes sense. Right? We're going to have the ray origin x times, the ray direction x times the ray origin x, and the ray, right? It just gets purely factored out, because all it's doing is providing a constant that doesn't actually change the result there. And again, that's exactly what we would expect, because really, you would just factor it this way. Even if that wasn't true somehow, we would just factor it this way. where we just start with curse LP, right? So we kind of know that that's just possible for us to get rid of. We know that that's possible. So we really just can concern ourselves with a very straightforward thing, even, more straightforward than we have before, which is that if we assume that this whole thing doesn't have to be relative to the origin anyway, because we could, even if we cared, we could just presuppose that it was aligned in that fashion, right? We know that this comes out of the equation. So then we get the next question, which is, well, what happens if we just don't consider, like, what happens with curse LP? Right? What happens with curse LP? So the reason that the thing changes with curse LP is because the decel X part is different, right? It's this part. So we don't know, because that part actually isn't constant through everything, because some people have decel added and some people have decel Y added. You know what I mean? I'm not sure that that will become a completely superfluous value, right? It shouldn't be able to be a completely superfluous value. I wouldn't assume. So I can't think if I'm missing something there. I don't think I am, but if you were to plug in for X step, like if you were to plug in cursel, right? I feel like there's still one thing that I'm missing here. So, let's suppose that I simplified this nomenclature slightly so that it doesn't take up as much space, just so it's easier for us to play with a little bit. You know what I mean? So if you imagine that you were going to expand this to so those are some shorter versions. So if we imagine that we were going to expand these two by saying, like, okay, we're going to plug in the cur p plus dx into x step p. Right. So we're gonna do that. Then when we multiply that out, we would expect to see this, right? Distribute the dir y, then distribute the dir x, and you get something that looks like that. So negative dir y times cur px plus dir cur p. I mean, right? Like, I don't think I'm missing something here. I'm not very good at math, as anyone who watches the stream knows very well. But, you know, that is... So it's kind of like, you can see the cross product reemerge, right? Like, you know, the perp dot product, you can see, you know, it looks like a cross product now, right? So if you look at what happens there, you figure, well, we're looking to see absolute value wise which one of these is going to be, you know, different. Let's see what happens when we do the same thing for the y step. If we substitute in cur p plus dir y, what we... Oops. So if we substitute in this for y step, like so, then we have our dot x's and our dot y's, and you distribute the dir y in both cases, like so, and the dir x in both cases, like so. And then if I group the terms the same way, then it looks like you have sort of that same term. It looks like you have like the same exact term in both as well. Right? So it seems like you're really just computing this one value, unless I messed up the math, which is very likely because it's me. It seems like if it wasn't inside an absolute value, you could actually just eliminate it, right? But because it is inside an absolute value, you can't, because you don't know whether this would have caused it to cross over a line and bounce back, right? The absolute value is makes it so you can't extract that. Right? We could fold the other one in so that there's only one, but one, like we could fold in the ray origin, but we can't eliminate the term entirely. So you have one term here, which is this. This is like dir cur p or something, right? And dir cur p can be shared between the two, but it can't be eliminated, I don't think. Right? Does that make sense? So I think that we are, you know, this would be very low cost, which is why I'm just thinking to myself, like, surely we can get that as fast or close to as fast as the table lookup. You know, it probably is slightly slower because, again, we have to maintain a few extra values, which is probably not free. You know what I mean? But the math is like very simple, right? So like if we are correct here, we're down to literally this. You know, so that part, that's the entirety of like what we would need to compute. We would need to compute, some multiplies, not very many. 1, 2, 3, 4, 5, 6. They can be done in parallel. So if we could pack these creatively, we could probably do like all of these multiplies at the same time. You know what I mean? So that's pretty easy. And one assumes that you can just save the value of the one you keep. So the Duraker p value is the value of the dot product with that thing, and you know that the new dot product is this one. So you also don't have to compute this, right? You can just keep it. So whatever you compute for these values in here, before you absolute value it, I think you can also just keep. So this only happens like at setup. So you compute like this one time. And then from then on, you are only computing these two values and keeping one of them. I think. Right? So I don't know, like, if that makes the difference. But if you look at what's going on here, you would think to yourself, like, okay, that doesn't seem particularly onerous. We have some setup. We literally just do this, and then based on the absolute value of between those two things, that's all we need, and then we can take the step and preserve the value for the next time. So I can't say that doesn't seem particularly onerous, right? Like that doesn't seem particularly bad. Like that seems pretty cheap, right? I mean, I don't know. So that seems pretty cheap. I don't know. That like I think we should just do that. So now you have another thing here, which is that like if you look at what happens with X step and Y step V, it's actually cheaper even still than that. Because really you know that the direction that you're stepping is on the grid. So the dx step, by definition, doesn't have a y value, right? Like this can't be in the equation because dx is strictly a move in x. And the same would be true here. So like there'd be no y value no x component of the y step. So you're really just looking at this, I think. Right? Like you're doing 2 multiplies, and you could roll the dy y value could have the negative rolled in, or actually the dx x value could have the negative rolled in. So the could both be, you could do this wide, you do like 1 multiply, 1 add, and then the extraction is unfortunately expensive, like, right? You know, maybe you just don't get much by doing it wide, but, you know, that's it. It's 4 ops tops. Then you do have to do a absolute value, so you've got an and, right? So yeah. Space naming, sorry, I'm not sure I followed you on that one. Dirker P is 2 times Dirker P plus dxy at the moment. I do not follow you there. Sorry. What? Oh, yes. You mean this. Gotcha. Sorry, I was looking up here. No, I agree. I just copied the grid index line and for some reason didn't change the plus. What I meant to say is, yes, we are preserving. We've computed the value, so all this is doing is just taking one of these two. Absolutely, yes. So I think that's the complete thing. So I'm gonna say let's just go ahead and do this. I mean, we have to be able to make that fast enough that I would think, right? And like I don't know, maybe the branch, maybe like the misprediction of like what happens with test is just too harsh. Granted, it can all be done with conditional move or something like that. Like there's no need to actually have a branch, but that still creates like a pipeline bubble, right? Like because it has to know what to fetch. But presumably if you put that at the head end, right? If you did that first, presumably you'd be okay. Wait, what's going on here? Why does my thing... Why is the... Okay, there it is. Never mind. Sorry, I thought there was a problem with the recording there. I want to make sure there wasn't. So I think we're good. I think we're good there. What time is it? Do we have time to implement this today? It's 2:22. Yeah, we probably do. Let's take a quick break, I guess. And let's go ahead and when we come back, we'll try implementing this, and then we just won't debug it. Like, we'll type it in today, and that'll be it. Like, we won't actually... We'll just get the code structured right, and then next weekend we'll debug it. Okay? That seems fair. So everyone take a quick break, and then we'll be back in a second. right. So I think that's it. And yeah, like I don't know, maybe I oversimplified that and I'm missing some details there, but that seems about right. Like that seems like pretty straightforward to me. I don't know. So we'll see. We'll see when we actually go to do this. So I'm not as centered as I should be, I feel like. I feel like I should be a little more centered here. I'm not as centered as I should be. In the webcam, I mean. Maybe the camera needs to be offset. Sometimes the puss play with it and it gets shifted over. So I probably should shift the camera a little bit. But oh well. Yeah, like you look at, if I look at the camera here, like basically, right, this is where I would normally be, so it's like it got shifted all the way over here. So maybe the real answer here is the camera needs to be rotated slightly. Let's just do that. I feel like that's going to be a little bit better, yeah. Now, does that create some bad, like, did we get off frame at all? No. So that's just fine. Yeah. Who knows? Who knows what happened? I usually assume that it probably is the puss. The puss, they go nuts at night. They run all around. And you end up in these situations where they probably bump into the camera. I have wanted to, for a while, mount the cameras on something more permanent. Like, basically, like, the equivalent of, like, a monitor arm that I drill into the wall or something. You know what I mean? Where, like, the camera can't be bumped. But right now it's just on a tripod, and the puss could knock it the whole way over if they wanted to. It's just not that stable. And so at some point it probably would be a good idea to like figure out how to like get that more aligned permanently. Like it's just like it won't now move because it's, you know, arc welded into place. But anyway, so let's take a look. I don't know. I'm a little nervous about this. I don't know why we still have that in there. We don't have our own absolute value. I assume that gets inlined properly, but I don't know. We'll find out. So if we have it all, if we look at what we need to do here for setup, the primary thing that we're missing at the moment is like, obviously the cur P is the ray origin minus the starting cell. Our initial problem is we don't have the starting cell really. I don't think, maybe we do, but I don't think so. So like if you look at what we get passed down, it's like this initial grid index thing. This is kind of a holdover from the way this code used to work. So I think what we more want to do is stop passing these two things and start passing actual like position values that we can then use. So yeah, it would be looking in full cast, which is now these are rapidly collapsing where we don't really probably need full cast anymore, so there's that. But if we look at full cast, you can see like in full cast, it gets past these values, which it then like slaps down. Like it's calling things like get quadrant for that don't actually need to happen. So basically like what I could do here is take this code and move it into like I could basically just finally collapse these routines entirely because there really is no reason. You can see here that like grid raycast is just a thing that happens at the end of this code. So these routines don't need to be separate anymore. And like they were separate because we used to just call grid raycast multiple times. And now we just don't even do that anymore. So at the very least, we could say, well, quadrant index, that's the easiest thing to replace. Quadrant index, literally, it could just be sent down as part of the remainder thing. The remainder is the atlas step part. Like again, this is all kind of stupid, but just trying to figure out like the slow movement of this into the other system. So we just need to know like where this thing is inside the outer cell, right? That's all we're really looking to determine. So the remainder would really be that. It tells us exactly where we are. And I'm pretty sure that it just doesn't get used anywhere, right? Like, yeah. So, if we wanted to, this whole situation could just be placed into the grid raycast code as a start. Like, it's not everything, but it's a start. So if we take remainder z and the quadrant index, and I drop those in here, so we've got something like this happening, and remainder, which is atlas index minus 2 half atlas index, that nonsense. If we start passing a remainder down, that's just like the simplest first step I can take. That's all I'm looking for here, is like the simplest first step I can take. So we pass remainder down, and now we have the information we need to actually do, without changing anything, we can do our stepping. So that's good. And this part of the code that we sketched out, I'm just going to if 0 out, because this is, we're just starting here. And so then now, instead of passing quadrant index, we're just going to pass the remainder, and compute quadrant index inside. No. There we go. So the code shouldn't change, I don't think. It's now like just going to run exactly as it did before, but the only difference is that we now, the only difference is that we have, you know why that's marked inline. Probably very old school. Yeah. This is still running, amusingly. And the lighting still works just fine, right? Which is what you would expect. So we can then look more carefully at this and say, well, okay, with the remainder now, we could start doing this other stepping. And what I'm going to do is, before like tearing the old code out, I want to be able to run them both together, because if I can run them both together, then I can more easily debug like the new one, right? Which seems like strictly a plus. So what I want to do is I want to get that, so, this grid raycast past the remainder, I want to get the values we were using for compute walk table, which I then, I hope to remove. You can see that the starting location, relative to the ray index, or relative to a cell, I should say, is going to be something like this. It's the cell dimension, with the remainder factored in from the divide, right? Something like this. Now, I don't know that we actually need to quite do that, because in theory, we know the starting cell, I think, because we have, like, I guess we could just call it with the atlas index. And we have the starting. So, you know what, now that I think about it, I wonder if we can just get rid of... We probably just don't need that, and we will be able to get rid of quadrant index once the other code doesn't use it, but it has to stay in there for now. If we have initial grid index, presumably you have to be able to back that out to get an atlas location, because if you couldn't, how are we sampling? So that must be something that is knowable. Let's take a look inside the spatial partition stuff here, which I believe is this code here. So, like, flat index from is the code that I think is being used here to index into this voxel, I think. And it looks like this does the opposite. Right? So again, we really wouldn't want to be doing this normally because it's too expensive. Oh, and you can see us doing it right here. Right? So you wouldn't really want to be doing this. We'll want to fix this so that we don't actually do this eventually. But for now, because we want to run these in parallel and don't want to rip out the other code, we can just recover one from the other, and it's not per ray, it's per cell, so we wouldn't really even notice, but this is definitely to do remove this way of computing the local ray origin, right? So again, our entire goal is to compute dir cur p. We know the direction x and direction y always because that's just the ray direction, right? And the ray direction, we have ray origin single, and the ray direction is going to be coming from this when we select this piece out. So it's ray d single, this right here. So in order to set up our dir cur p, this value, which is for stepping, maybe I'll call that stepping cur p or something, right? We know that when we set up the ray index before we enter the loop, that value has to have the ray d singles x value and the ray d singles y value, which come out of these two, times cur p and cur x. So those are the two values that we actually need. And to compute those two values, what we said is they have to be the ray origin, the cell center of the starting cell minus the ray origin. Now, we know the ray origin. It's constant forever because until we exit this routine, we don't move the casting location. So this ray origin this ray origin single is the value we actually need for that, right? But we additionally need for that cur p, right? So the ray origin singles xy is going to get subtracted away from the cell center xy, and it's that cell center that we don't know. You know what I'm saying? So we need this. So we need like stepping, initial p. Whatever that initial stepping value is, that's the thing that we actually needed to compute. We have part of it. We don't have the other part of it, and that is the part we're computing here, right? So we don't really need get cell bounds. We just need get cell center. I mean, probably we don't care because, like I said, right now we're just reverse engineering this for testing purposes anyway. So I would assume that, this is fine. So get cell bounds. It looks like we could have just called instead get cell center p, which is fine. And that gives us I think that gives us what we want, which is cell center. And again, we don't care about the z value. It's right, it's irrelevant. Oops. Now maybe I shouldn't do it that way. Maybe since we're doing xy's here, maybe we'll make it clear. It's like those are the xy's. Yeah. So that's the entirety of the setup code, I think. Which is to say that this stepping bit here before we enter the walk iteration, it's just that piece of code goes there. We then have the walk code, which is this code in the loop. And in here, this would just be at the end. This would be how we would decide to move. So previously we were doing this move, which is, looking up the walk table by, by looking up the walk table to get what cell you move to next. And here we would instead be taking that dir cur p value, which we step up here. We change it to stepping cur p. But so that stepping cur p value The ray direction is just called ray dir single, right? I think. It's this. Okay. So this code here, instead of dir, is ray dir single. And the dx and the dy are how far apart these are. So this is just like voxel dim x and y, right? But the problem that we have, and so why we need to introduce a separate value here, is we don't know what direction we're stepping in, because we would need to know the sign of the value first. So, because the ray, we only are considering one kind of step. We don't look at like left and right or up and down. We only look at if the ray is going leftward, we look at stepping left. If the ray is going upward, we look at stepping up, right? We don't look at down if the ray is stepping up, and we don't look at right if the ray is stepping left. So we really have to compute here, not compute here, but store at the outset stepping delta x or whatever and stepping delta y, which are going to be like, we don't have to compute this every time. They're just going to be like a fixed value, like so, that we add. Because it doesn't change the amount that you step in x or y, you always step by one whole grid square. So these are computed a priori based on the ray direction once it is known. And for each step along the grid, we don't need to like recompute that. So it's literally just this. And then these dx, dy values are just the sign. They're just going to be like the sign of the ray direction. So whatever whatever the sign is of the corresponding ray direction, and I don't actually know I think we can just call this right here, right? So the sign of is all we really need here. So it's really like sine of the other one. It's times the sine of whatever the ray d single is, or the ray of the opposite one. So, you know, in the y step case, it's the y. So we have the ray d singles x times the sine of the y times however big the voxel is in that direction, which is just cell dim. Right. And I think that's it. All we need to know now is, oh, this is stepping curve P here. All we need to know now is how far you would move in each case, and that's the end of it. Again, really simple code here, right? If you look at it, you know, who knows if we did it right? We might have bugs. But in terms of conceptually what actually had to happen there, it's pretty simple, and there's not a whole lot of code, right? There's not a whole lot of code involved. So that seems to, you know, that seems to bode well for what we're looking at here. So walk table entry, walk table entry. So the S16s that we use here for our D grid, which could just be S32s in this case, because we don't care about how big they are now, since they're just going to be like local. They're not stored in a table, and this will hopefully go away. So at this point, those values are just going to be whatever the actual span is. We know this from compute walk table, right? Like whatever the actual span is, it's step best dim, right? That step value. And so we need that. I suppose the problem we get there is it has to also be, it has to correspond to the sign correctly again, right? So that does it is a little bit annoying. It's not as free as we would like it to be. Right, so we have the voxel dimension, like the spatial grid. And I don't know. The voxel dim for the spatial grid is cell count, right? So the cell count x is how much you would move in x, and the cell count y times the cell count x is how much you would move for a d step in y. And those two would both be, you just need to negate them. Like we can just, these are, just basic values. And the problem is here you've got this sort of sign, you again have to do this sign check, which seems bad. The sign of one doesn't seem so bad, but this one kind of does. So these have to be selected based on which direction the ray goes, which kind of sucks, right? Because it's a float check. You've got to like send the sign bit over. You know what I mean? Which is not good, right? So you have this nasty problem of now you're doing this, which is ray d single x. If it's less than 0, then it's d grid index x base. Otherwise, it's d grid index x base without the minus, right? That just is crappy. There's really no two ways about it. That's not good, I don't think. So we probably need to figure out a better way to do that stepping. Like, it might almost be better to, like, do it in the SIMD registers and then just move the value out just one time to do the lookup or something. That just seems bad to me. You know what I mean? That just seems... That seems not good. Is grid index an S16? Is that the yeah, it is. Okay. Fine. I don't care. They can be a 16 if you want. We'll probably change that eventually, but... So, okay. Oh, whoops. Okay. So yeah, at this point now we have the problem of we can't actually run both of these codes at the same time and actually add to the real value. So I probably need to introduce a synthetic value here that we're checking, right? Because I can't add to the grid index twice. That would totally break. So we probably want a grid index that's like our check grid index here. That now we can go and see if this produces similar results at all to the other one that we had. You know what I mean? And so now if we run it, it should have the same behavior as before because all the lighting should still be running through the same path as it was previously. There shouldn't be any difference, right? And so if you wait until that annoying part of the bug goes away, then we're fine, right? And it should just be the same as it was, which it does appear to be, right? And then if I go and I say, let's switch to the debug version of the build, and we build, I would go ahead now and say we should be able to set a breakpoint and look at these step differences to see what we end up with, right? So like at this point in the code, we have a check grid index and a grid index, and we should be able to now like start to debug those. You know what I mean? You know, I just realized that everything I just said to you was a total lie. I have to remember to update remedy, by the way. That bug got fixed where it doesn't stop the executable, and I just forgot to update. We should update. So we hit that occasionally. I just realized that's totally wrong what I said before. This dgrid index x, it's the other way around. So the y is the one that steps by x, and the x steps by 1. I don't know why I did a z step there for some reason. That's just, you know, addled brain. So let's try that one more time. And I don't know if I probably still have to set the breakpoint. I think I may have removed it. But I still want that breakpoint in the lighting code, please. So let's go back and reset it so that I can look at those two together and look at the differences between the grid indexes. So like same piece of code. And I just wanted to look at these. So we're looking at the difference between check grid index and grid index. This looks off also. So it's bad. But hey, look, they're pretty similar. They're actually exactly the same. So let's find out if this turns out to be roughly correct most of the time. Let's see how often we hit an assert designed to catch them diverging. So if I go here and say assert grid index equals check grid index, like how often does that hit? All the time, a little bit of the time, sometimes, etc. And I don't know. So we're going to find out how often that assert hits. I definitely have to go. Let's just update remedy while we're here, because we do need that to be patched. So hold on one second. I will grab the new version, because like that was causing us a huge amount of problems, and there's no real need to keep suffering through that. So let's go ahead and pull down an itch.io. Where is remedy? No, remedy is somewhere. There it is. So I will download the latest version, which is 3.6.4. And I will save that to the drive. I will then take that said drive and plug it in to W apps. It's in here, right? Yeah, remedy BG. So I will go ahead and just copy this over And I think that should do it. So that should be all we need to fix that problem, which is good. Hopefully. And back we go. So I open this up, I run it, and I just look to see whether this hits often or not often. You know what I mean? And furthermore, are they off by like one step or are they off by like a lot of steps? You know, and I don't know. So that looks pretty bad. I'm not sure what that would imply exactly. It's just, okay, so it just picked differently in this case, I guess. So honestly, that's a really hard one to call. I don't even know if that means that anything is wrong here. That could just be when the two ways of checking diverge, which might be fine. Also, the other one is potentially buggy. So it's like, eh? So I would say, I'm just curious, like, we'll save this for next weekend, I think, in general, but I'm curious to know, like, what happens if we just swap these two, you know? So we go, like, all right, grid index is now updated by our weird one. And good luck. You know, what happens? How bad is it? How far off is our new routine from our old routine? Is it an absolute disaster? Slight disaster? Of course, I guess this doesn't really tell us much because we're still running in slow mode, so we're not going to see like a huge amount of anything really happening there. But all right, so now we're like not really using the walk table except to compute t-terminate, which is something we will have to address later. But you know, now we're in theory operating without that actual piece of the code, like without the walk table being necessary to do the spatial lookups, right? And so we can sort of see what happens with that. I don't know that we would expect much difference, but it is just one nice step forward, right? And honestly, are we still using instant update? We are. So that was the bug. The lighting tables actually are a bug. It doesn't mean we don't have another bug, but it does look like that particular bug gets fixed by getting rid of the walk table. Right? So our walk table was messed up, as we suspected, and I do think I made the right call because I think this is simple enough that we should be pursuing this one because it will simplify our lives, right? So t-terminate is still a problem because we don't actually have a way to update t-terminate at the moment. And I guess the only reason that we care about t-terminate at all, t-terminate was there for only one reason. And like t-terminate was only there so that when you run out of time to sample something, like you've gone some distance and you haven't hit anything, where do you actually sample the lighting from at that point? And one answer is you don't sample it at all, but the way we chose to do it was, look, if you check that far away from where you are right now, eventually what you should just do is sample the light that's at that place and consider you getting the same light convected forward to you, right? Now, we were doing that because it was expensive to do something else. It's possible that we just should consider that ray to have not hit anything and don't actually run the rest of the routine. That's possible. If we look at what happens with t-terminate, for example, here, it's what is used, right? Like, we use so probe sample p single, we use what ends up being the anyway, I had a thought there, but I'm not gonna think that particular thought. So anyway, if you look at what happens here when we look at updating probe p sample singular, right? When we go through here and we do, like, right here, you can see us actually doing the raycast test. Excuse me. We end up in a path that's like, did we hit anything? In the path where we say, like, did we hit anything, we update where we're going to sample using this code. So it's this, right? Probe sample p single. Excuse me. So the question is, when we would normally fall out of this loop, what we used to do is just say, well, whatever the termination location is for this thing, so all we really need is some way of ensuring that we know where we would sample from. And we kind of know that. Like, we could just consider that location to be wherever the cell center currently is, which we sort of know. I mean, we don't really know. We'd have to keep updating it, right? So it's like, also, when this terminates, probe p single would not be... Yeah, so I can see why this wouldn't quite work the same way. But yeah, you could just say, look, probe sample p single... What if it just never gets updated? Like, what if we just don't do that? What if we just don't sample, we don't use that convection process? Is that just better if we don't do that? Probably not, but... So I guess what I would say here is, well, we know what grid cell we're in, and we could just sample from that grid cell, I guess. I don't have a good idea here, right? But if you end up on a terminator node. So, you know, something like this, I suppose. If we've gone too far or we hit the end, then we need to have some value that we like can step forward to. You know what I mean? And the question is, where should that be? And, you know, maybe the answer is we should just unpack the ray index. Like, we should just get wherever we are in the thing and unpack that. Or maybe the answer is we track a t-value forward as we step. I don't know how smart that is, though. I mean, it's not that hard. It's not that hard because you know a priori how much each t-step is. So, you know, if you looked at t-terminate here, it's the same value either way. Like when you take a step forward, you know how far in t the ray has to go to move to the next cell over, because you know how far, you know the dot product of the cell volume with that t value. So, you know, I can't say it's like my favorite thing in the world, but you literally could just have one more of these that's like that. And it's just, it sucks because you've got too many things that are like updating at that point. Like there's just too many values here, and it seems like you probably would rather have less of those. But that's really all you would need. So if you assumed that you took t-terminate and you said, well, we're going to start out by saying, where is the t value along the ray for this cell? Yeah. So you basically say, like, t-terminate initial. And you know what that is. It's just the inner product of the cell center minus the ray origin. Times the ray direction. Sorry, ray d single. So in other words, to step to the current center, we're gonna step like forwards or backwards. It might actually be backwards if we're pointing in the wrong direction. We're gonna step backwards in t to hit that. And I guess we don't even need to talk about it as t-terminate initial. I guess that's just t-terminate, right? It's literally just this. It's t-terminate. And that's just it's just this value. It's that value spammed. If we want this to be wide, which apparently we do, then it's just that value spammed. Like so. I don't know if we have one that lofts up the entire thing. Yeah, it's just, yeah, if you just pass one. So, like, you know, it's literally t-terminate would just start out at whatever that value is. I think that's just free. Did I mess something up there? Syntax error semicolon. Oh, sorry about that. So we really just need to know the two inner products with the ray direction for stepping the other way, right? So the amount of change, the distance along the ray you go in each case is pre-computable. So the T terminate step, it's always forward. And it's always going to be the inner product of whatever the ray direction is times a particular step. Now, it's not really even the inner product because you don't actually have to do the entire thing, right? It's literally always going to be 0 everywhere except for the one type of step you're taking. So when you talk about like the cell dimension, if you're talking about how far do we go along the ray if we want to take one cell dimension X step, well, the answer is you're just going to take that times that component of the ray direction. Like that's it. Because all the rest of the values for cell that you're stepping 0 in the other directions, right? So I believe it's literally just those two values. The ray d single in this case is just you don't have to compute a full dot product because you know that the cell dim is you're only stepping along one axis of the cell dim, the other ones are going to be 0. So it's always just going to be that, minor change. That's all that happens. You don't have to do anything else to compute the actual value. So, yeah. So anyway, when you do T terminate, it's just going to do a step, and we need those to be things we can add together. So I don't actually know what because this wants to be an F32, I don't know that you really actually want to bother with keeping it as an F32-4X, but for now I'll just do that because that's what it apparently wants, so that's fine. These values just have to be expanded. So when we can initially compute what these T terminates are, we need to wrap them so that they're replicated 4 wide, so that they flow through the 4 wide path, right? But that's it. Whoop-de-doo, we now computed T terminate. And so now we can also do the same check that we were going to check before, which is to see whether or not it actually seems like it lines up with the correct values. And I don't know. It's not going to be the same anyway. But either way, I would say, look, if we just turn off this now, so T terminate is only being updated by us. I want to say that will probably still work, maybe. But of course, it's hard to know because our lighting still has the other bug in it. So, who knows? But I want to say that you wouldn't see any real difference in here at that point. But, maybe there's other problems. I'm not sure. So I want to say, and I'm just going to make this command decision because, hey, it's the end of the stream. I say we just pull out the walk tables. They're completely gone now. And we call it a day. So walk table gone. Compute walk table is gone. I'm just getting rid of all of it. And it's considered unacceptable to have walk tables now because we made that so simple that presumably it just doesn't matter anymore. So I'm removing 100% of all the compute walk table stuff. All of that's just gone. The sample direction table is still there at the moment. But where does that get copied? Should that get copied? Oh, it looks like that push array does the copy, I guess. No, it doesn't. So when does that get copied? Did we copy that in the walk map version? If so, we should probably get rid of that, in fact, entirely. Like, we should also just get rid of the sample direction table thing and just use it instead of, use the actual baked one. So in the INL, like this thing, sample direction table, and now it's just a v3, right? It doesn't have any other intervening data. So the sample direction table now is just a static piece of data. We don't allocate anything to store it or any of that sort of nonsense. So I think that's the end of that. Right? Okay. So now in theory, we're running completely without walk tables now. I don't know how the profile's doing, but it seems like it's roughly where it was. So I think that's fine. We could probably actually do some optimization work at some point because now we've simplified things quite a bit. There's probably a lot of cruft we can pull out of here. But anyway, we're still at 30 frames a second, even with the debug system running in no particular. We even have like light validation is still turned on. There's asserts are turned on. All of that's still turned on, and we're still running at 30 frames a second with the full global illumination running. So I would call that a pretty reasonable victory. The lighting looks awesome. So I think we're down to now just one bug, which is our light leak, that like over-brighting weird nonsense that's happening. It's very strange, right? You can see it gets that weird like why does that movement, change the total brightness of those lights? Like, it's very strange. So we have one more really pretty serious bug, unless it's a confluence of bugs. Maybe there's more than one bug. We have one pretty serious one, so we've got to go take care of that. But otherwise, it's looking really cool. Like, love the look of it. It's running really quickly. So that's great. And we removed the walk tables, which means we could add entropy back in if we wanted to for free. So basically, we're down to just one more. And that's what we'll do next weekend. But at least we got rid of the walk tables now as well. So we could also, that means get rid of this entire table in the pre-compute. That entire thing could go away as well. And we could just use like white noise entropy or something that's, low cost and try that out just to see what happens if we do that. And, we might want to do that as a thing that allows the lighting to be scalable, better, more scalable, right? And perhaps have less artifacts due to directional issues. But overall, I'd say really looks really good. And remember, that's without smoothing. So there's no that's 100% temporal anti-aliasing free. It's recomputing the entire lighting for the entire system on every frame. And so we're in really good shape if we can just go eliminate whatever that last energy leak bug is. We would get lighting that looks like this, and it's instantly updated. That there's no temporal smoothing applied to that at all. So that's great. Like, that's really good. Because that means it would update instantly to lighting changes, right? There's no lag on the lighting, right? Which I think is pretty cool. So, I think we're in really good shape, but it's, that energy bleed is going to be hard to track down. Those are kind of really tough sorts of bugs. So, unfortunately, that's not going to be an easy one to find. But I'd say that's it for today. That was pretty good work. I think I'm happy with that. I think we can. Yeah, I think we'll be able to simplify the lighting system even more now because we just keep removing pieces of it and it gets better, right? So that's a really good place to be. We can probably simplify some of how these loops work and just get stuff down to a more minimal state. And as we do that, it also gets easier to find the bugs in it. We're still spending a lot of time doing the octahedral map downsampling. That's if I remember correctly, still a really big problem. So there's that. But not having to have the lighting, not having to have that, the walk tables and the pre-computed stuff is just really nice. So I think that's probably very good. Like, we're probably in really good shape here, is what I would say. But yeah, like the diffuse weighting stuff is still really expensive. Like, so I want to say that probably the raycasting is now, like, you know, fairly expensive because we're doing a ton of it. Like, we're doing, again, no temporal smoothing, so we're doing a ton of raycasting. Lots of rays per octahedral map sample. But I don't know. I don't think we separately at the moment break out how much time is spent in smoothing out the those maps. So I don't actually know, like, as you can see, all the time is spent in the lighting. Like, the entire game is spent, all the CPU time is in the lighting, which is what you expect. But I don't even know how much of that is actually raycasting. You know what I mean? Like, if we were to go into the raycaster and we were to change the raycast to be operating on way less rays, so like we just said, oh yeah, like actually, you're only gonna cast like one ray instead. I don't actually know how much of a speed improvement that gets us. Like, maybe a ton, maybe not. I don't really know. So yeah, like compute light propagation work, like how much does that go down by? Like 3, so that's around 30 million cycles, is that right? Comma 30 million cycles. And so now it's 400 million cycles. So it's a little over 10x the cost. I could probably do it exactly by just saying, like, okay, we remove the raycast. And it's around, what is that, 8 million cycles? So I guess it is mostly in the raycast now. That's actually good. So I guess we're not, somehow we managed. Was that really true? I thought it cost more than that. I don't know that I trust those timings. I wonder if maybe, like, actually it was able to optimize some of that out of the smoothing. I don't know. So I'm not sure how I feel about those timings. Take that with a grain of salt. But anyway, point being, at 30 frames a second, we would expect here that we could do a fair bit. We can also change this rays per texel value at the moment. It's doing 16, right? And if we did half that, we would expect to still probably be able to have okay lighting if we added some temporal smoothing, and we get a pretty big speed up. So, oh wait, not times, that's not what I wanted. So we would expect in general to probably be able to have a fair. Oh wow, that's cool. Yeah, the bug is so interesting. Like, it clearly has something to do with direction as well. That's really interesting. It must just be some stupid bug. Like, yeah. But anyway, you can see here that, like, the lighting at half the samples is basically the same. It's going to be darker because obviously we're dividing by half, but other than that, you know, you just don't divide by half. If you actually just set this value here to something else, so like this ray weight value, right? If I said divide by 2, and oh, by the way, also multiply the output by 2, The bugs are so interesting, aren't they? I can't wait till we find out what this is. It's going to be very interesting, because how are we getting those? Like, they're so structured. They're so structured. Like, it's going to be very interesting to find out what that power leak is from. Very interesting. It must be that, like, the direction you're casting, like, erroneously writes into, like, I don't know, there's some kind of weird, like, the direction. I wish I could think of, like, what that would be. What's that gonna be? I bet we should kind of be able to figure it out. I just, for some reason, I just can't quite. Yeah, I don't know. I can't quite figure out what that's going to be. But point being, I think the lighting would still work just fine with less samples. And we already know that with half the samples, we'd be running at 60 frames a second, even with all the debug code in place, right? With the debug code not in place, I don't even know, like, if we turned off light asserts, or if we... Because actually, I suppose at the moment we actually do want those off, because we're not really doing anything with that at the moment. If we turned off those asserts and we also turned off the other internal asserts, I don't actually know how fast we are, but probably pretty fast. Yeah, I mean, we might actually be, with everything turned off, I'm not sure, we might actually be 60 frames a second, just even with 16 samples per texel, which is nuts. So, hey, computer's very fast. And this is on an old computer, which is kind of nuts. And it's all on the CPU. So, computers, man. You would think if you run a web program, you would think that it would be that computers are super slow. But when you actually run code that does a lot of work, it's actually nuts, because you look and computers are actually incredibly fast. Like, the amount of work we're asking it to do is insane. You know? So. So, you know, not quite there. 24 milliseconds frame. We need to be at 16 milliseconds frame. So who knows? You know, maybe we need less samples to get there. Maybe that's too expensive, but who knows? We got a long ways to go before we determine stuff like that. But yeah, it's so really weird, just whatever that last bug is. It's going to be very interesting to see what it is. But all right, that's it for today. Yeah, if you use like a web browser, you'd think that computers are really slow, right? But actually, computers are incredibly fast. It's just the programs that people write are incredibly slow for no real reason. Because, you know, this is just kind of a tremendous amount of work we're asking this thing to do, and it just eats it for breakfast. It's kind of nuts, right? So. Yes, Jur33, that's exactly correct. The GPU shaders basically just sample a voxel. It's a little more complicated than that, because the thing that is actually getting sent down is an octahedral map, so it's not the same as a voxel sample per se, but it is basically a voxel interpolation. Like, at each node in the voxel, at each node in the 3D grid, there's an octahedral map for the inbound light at that location. And that would be the GPU is having to interpolate between 8 samples of octahedral maps. So you can think of it as the GPU samples an octahedral map at each of the corners of that cube that it's in, and then it interpolates the results, if that makes sense. I don't know if that makes any sense to you, but that's what it's doing. And so the CPU does all the lighting. The lighting could be moved to the GPU. And we might do that someday, but I think it's better to do it on the CPU for now because it was a very complicated process to figure out how we were going to do it. And if it was on the GPU programming is just really sucks. It's hard to debug. It's a lot more finicky, right? So doing it on the CPU seems good, and then if later you want to drop it to the GPU, as long as you've been programming it in such a way as it's expected to be parallelized like that to a certain extent, it's probably not that bad. But another way to look at it is CPUs are starting to have a lot of cores now, and what are you going to use those cores for, right? In a game like Handmade Hero, there's not a lot of other stuff going on, so having it do the lighting means there's more horsepower on the CPU, on the GPU to do other things, which maybe just means, you run at a higher resolution or whatever. So I don't actually know whether it depends on the game. Some games may want the lighting to run in one place, some want to in another. The fact that NVIDIA cards are now adding ray tracing means that at the limit, Handmade Hero 2030, you probably want to run this on the GPU because it's got ray tracing acceleration, right? So it kind of becomes a no-brainer at that point. But in the interim, it's probably hard to say. It is not a spherical harmonics encoding. It's literally an octahedral map. So it is a encoding of, if you imagined a sphere and you broke the sphere up into 8 octants, and then you stored texels at a certain resolution that actually that are just what the inbound light is at those positions on the sphere. So spherical harmonics is very different. Spherical harmonics is when you store a set of coefficients, and the coefficients are basically, they multiply basis functions that are 3-dimensional lighting shapes that you then compose to determine, usually compose and then take the dot product with some direction to determine what the lighting is in that direction. They're very, very different, right? It's equivalent to the difference, like an octahedral map is just storing the lighting directly, like how much light is coming in from each direction. So it's a lot like octahedral maps are like an image, and spherical harmonics are like the FFT of that image, kind of a thing, right? It's that sort of a difference. One is a series of coefficients on basis functions that affect the whole thing, and the other is like individual light values coming in a different texel. So octahedral maps are way easier to understand than spherical harmonics visually, because human beings are not really used to thinking of things as additions of lobes, right? You don't tend to think of things as oh, okay, the inbound light is this shape plus negative of that shape plus positive of this shape or whatever, right? It's not how you think of things. It's way easier to think of oh, the incoming light is these color values. In that direction, it's this value, and in that direction, it's this value. So an octahedral map is much easier to understand than spherical harmonics. It might not be as good to compute with. In certain situations, spherical harmonics may be way more efficient. But in terms of what you would intuit, an octahedral map is fairly straightforward to understand, whereas spherical harmonics are much more difficult to just intuitively think about what's happening. If you saw it. Looking at the 3 numbers of spherical harmonics would be impossible. You'd just be okay, I see 3 numbers, I have no idea, what the actual lighting looks like. I mean, you might have a vague sense of okay, the first one is the average light that's inbound, so that's pretty easy. But then it's okay, that one's sort of telling me roughly how much light comes from that side versus that side. It's the sidedness of the lighting, right? So you could learn to interpret the values, because they do mean something, but it's just not very directly translatable to you. The first 2 coefficients, 3, 2 or 3 spherical harmonic sources are probably not that hard to understand. But as you start getting down into lower ones, it's like, okay, yeah, I know what they are, but intuitively, like, developing a sense for looking at 8 spherical harmonics numbers, what does that translate into in terms of inbound lighting is pretty freaking hard, I would argue, right? Now, I don't work with spherical harmonics very often, so maybe that's just because I don't work with them enough. Maybe if you work with them enough, you would. But I really do feel like, yeah, octahedral map's much easier to understand intuitively than spherical harmonics, which are much harder because you have to kind of reconstruct in your head what's going on every time. So, all right, folks, that's it for today. I will be back here next weekend when we will have to track down our final bug. I mean, there's probably other bugs in here, but the final main one, like the one we can see, right? So next weekend we will track down the final bug we can see, and then it's probably time to just say, okay, that accomplished what we wanted. Like, our goal was to simplify the lighting down to the point where we were happy with like it and it was fine. And I think that is probably it. So we can go on to the next simplification pass, which was not on lighting. That would just be simplifying the spatial stuff to be only one Z sheet. So yeah, like getting there, running very efficiently right now, looks great. So yeah, not a lot of complaints. There's definitely, is it a good engine? I mean, not compared to what would happen if I was actually concentrating on it, right? Like at such a small time investment in it and being so sporadic, there's a lot of things that are just like, all right, that's not as good as it should be for sure. But, in terms of the final look of things, it does look really good. And it does seem to play very well. So, I'm optimistic that there's nothing particularly bad about the engine that would prevent it from being, interested, right? So. No, Valbus. Z is just really makes things much more complicated. Like, you could add Z into the raycaster again by just adding one more check for movement in Z. But then instead of one test value and a CMOV, you now have like 3 test checks that have to then factor into multiple CMOVs or something, or you just use an actual 3-state if. Picking between 2 options is a lot easier than picking between 3 options, is I guess what I would say. So maybe it's fine if you add Z in, or maybe the code just keeps getting slower as the CPU struggles with that like multiple chained C move. Like, I don't know. So I don't know. So maybe it's fine, and maybe just add that in. But the real cost is not that anyway. Like, that's the thing that makes the loop nastier. But you could do it, and it's just a chain of CMOS, right? It's just like extra. The real cost is having multiple Z samples, because it just multiplies, a cubic volume of samples is just way more samples than a 2D volume of samples, right? And so really the thing that makes the lighting so much easier in 2D than in 3D is that you just don't have to compute times Z. Instead of having to do a stack of 8 things, you do a stack of 2 things that's 4 times faster, right? For nothing. Like, it's just a free 4x faster. So when you add Z back in, it just becomes a lot more expensive. There's really no 2 ways about it, right? It's just a higher multiple for anything volumetric like that. So I think that's mostly it. So adding Z back in, not hard. Slows down the raycast a little bit, but then the real killer by far, is obviously just, the extra Z sheets is way too many samples. It's way too many voxel cells. So, all right, that's it, everybody. I guess I should look to see is like John streaming or anything. Doesn't look like it. But anyway, that's it for today. I'll see everyone back here next week. Until then, have fun programming, everyone. I'll see you all on the internet. Take it easy, everybody.